Let's start now. Somewhere in the universe, a star is dying. Not slowly, not quietly, but violently. Imagine looking up at the night sky and seeing a new star appear out of nowhere, brighter than anything around it, bright enough to be seen across entire galaxies. But what you're actually witnessing is destruction. A star tearing itself apart, releasing more energy in a few seconds than our sun will produce over its entire lifetime. This is a supernova, and it's one of the most powerful events in the universe. What is a supernova? To understand a supernova, you first need to understand balance. Every star exists in a constant struggle between two forces: gravity, pulling everything inward, and fusion, pushing outward. As long as these two forces remain balanced, a star lives. But when that balance breaks, everything changes. A supernova is what happens when that balance collapses completely. In just seconds, a stable star becomes unstable. Pressure disappears. Gravity wins. And the result is catastrophic. Temperatures rise into the billions of degrees. Shockwaves rip through the star. And matter is ejected into space at thousands of kilometers per second. But not all supernovae happen the same way. Some are slow, building over millions of years. Others happen in less than a second. And some leave absolutely nothing behind. The life and death of stars. Building toward explosion. To understand why supernovae happen, we must first understand how stars live. Stars form in cold, dense regions of space known as molecular clouds. These clouds contain hydrogen gas, dust, and traces of other elements. Over time, gravity causes regions of the cloud to collapse, forming dense clumps that eventually become protostars. As a protostar contracts, its core temperature rises. When the temperature becomes high enough, millions of degrees, nuclear fusion begins. Hydrogen nuclei combine to form helium, releasing energy in the process. This energy creates an outward pressure that balances the inward pull of gravity. This equilibrium, known as hydrostatic equilibrium, is what keeps a star stable. For most of its life, a star remains in this stable phase, known as the main sequence. However, the duration of this phase depends on the star's mass. Smaller stars burn their fuel slowly and can live for billions or even trillions of years. Massive stars, on the other hand, burn through their fuel much more quickly, living for only millions of years. As a star exhausts its hydrogen, it begins to fuse heavier elements. In massive stars, this process continues through multiple stages, forming layers of different elements like an onion. Each layer represents a different stage of fusion, with heavier elements forming closer to the core. Eventually, the star reaches a critical point. It begins to produce iron, the iron catastrophe and core collapse. Iron is the key to understanding the death of massive stars. Unlike lighter elements, iron does not release energy when it undergoes fusion. Instead, it absorbs energy. This means that once a star's core is composed primarily of iron, fusion can no longer provide the pressure needed to counteract gravity. Without this pressure, the star becomes unstable. In a fraction of a second, the core collapses under its own gravity. The density increases dramatically, reaching levels comparable to that of atomic nuclei. Temperatures soar to billions of degrees. During this collapse, electrons are forced into protons, forming neutrons and releasing neutrinos. This process, known as neutronization, transforms the core into a dense neutron star. The collapse is halted when the core reaches a point where neutron degeneracy pressure resists further compression. At this moment, the infalling material rebounds, creating a powerful shockwave. This shockwave moves outward, slamming into the outer layers of the star. The result is a supernova explosion. Shockwaves, energy, and cosmic recycling. The shockwave generated by a supernova is one of the most powerful phenomena in the universe. Traveling at thousands of kilometers per second, it carries enormous amounts of energy into the surrounding space. As the shockwave expands, It interacts with the interstellar medium, the gas and dust that fills the space between stars. This interaction heats the material to extremely high temperatures, causing it to emit radiation across multiple wavelengths. But perhaps more importantly, the shock wave compresses nearby gas clouds. This compression can trigger the collapse of these clouds, leading to the formation of new stars. In this way, supernovae act as catalysts for star formation. They are not just destructive forces, they are agents of renewal. Neutrinos, the invisible signal. One of the most fascinating aspects of supernovae is the role of neutrinos. During a core collapse supernova, an enormous number of neutrinos are produced, far more than any other type of particle. In fact, about 99% of the energy released in the explosion is carried away by neutrinos. These particles interact very weakly with matter, allowing them to escape from the core of the star almost immediately. This makes them incredibly valuable for scientists, as they provide a direct glimpse into the processes occurring deep inside the explosion. In 1987, a supernova known as SN 1987A was observed in a nearby galaxy. Detectors on Earth recorded a burst of neutrinos from this event, providing the first direct evidence of the role neutrinos play in supernova explosions. Classifying supernovae, light and spectra. Supernovae are classified based on their spectra and light curves. The spectrum of a supernova reveals the elements present in the explosion, while the light curve shows how its brightness changes over time. These observations allow astronomers to categorize supernovae into different types. Type 2 supernovae show strong hydrogen lines, indicating that the star retained its outer hydrogen layer. Type 1 supernovae lack these lines, suggesting that the hydrogen was lost before the explosion. Within these broad categories, there are further subdivisions, each providing clues about the star's structure, composition, and evolutionary history. Type 1b and 1c. Stripped stars. Type 1b and 1c supernovae are examples of core collapse supernovae in which the star has lost its outer layers. This loss can occur due to strong stellar winds or interactions with a companion star in a binary system. As a result, the star is stripped down to its core before exploding. In Type 1b supernovae, the hydrogen layer is missing, while in Type 1c, both hydrogen and helium are absent. These differences affect the appearance of the explosion and the elements observed in the spectrum. These types of supernova are often associated with gamma-ray bursts, particularly in the case of rapidly rotating massive stars. Gamma-ray bursts, cosmic beams of energy. Gamma-ray bursts are among the most energetic events in the universe. They occur when massive stars collapse into black holes, producing narrow jets of high-energy radiation. If one of these jets is directed toward Earth, it can be detected as a brief but intense burst of gamma rays. These events release enormous amounts of energy in a very short time, making them some of the most powerful explosions ever observed. Type 1. A supernovae, thermonuclear explosions. Type 1. A supernovae occur in white dwarfs, which are the remnants of stars that were not massive enough to undergo core collapse. A white dwarf is supported by electron degeneracy pressure, which prevents it from collapsing under its own gravity. However, if it gains enough mass, this pressure can be overcome. This can happen in a binary system, where the white dwarf accretes material from a companion star, or when two white dwarfs merge. When the mass exceeds the Chandrasekhar limit, a runaway thermonuclear reaction begins, fusing carbon and oxygen in an uncontrolled manner. The result is a complete explosion that leaves no remnant behind. Pair instability. This type of supernova only occurs in extremely massive stars, often over 100 solar masses. At extreme temperatures, something unusual happens. Gamma-ray photons become so energetic they transform into electron, positron, its antimatter counterpart. This process removes radiation pressure, which is what was supporting the star. The core suddenly loses stability. It contracts. Fusion rates spike uncontrollably, and instead of collapsing into a compact object, the entire star is obliterated. No remnant remains. These explosions are so powerful, they can produce tens of solar masses of heavy elements. Element creation supernovae are cosmic factories. Inside these explosions, conditions are so extreme that nuclei rapidly capture neutrons. This process is called the R process. It forms a gold, platinum, uranium. Without supernova, no rocky planets, no complex chemistry, no life. Even calcium in your bones was forged in ancient stellar explosions. A supernovae have a consistent peak brightness, making them useful as standard candles for measuring cosmic distances. By observing these supernovae in distant galaxies, astronomers can determine how far away those galaxies are. Combined with measurements of redshift, this allows scientists to map the expansion of the universe. In the late 1990s, observations of distant Type 1a supernovae led to the discovery that the expansion of the universe is accelerating. This was one of the most important discoveries in modern cosmology and led to the concept of dark energy. Extreme supernovae. Some supernovae involve even more extreme physics. Pair instability. Supernovae occur in very massive stars, where high-energy photons create particle pairs, reducing pressure and triggering collapse. Hypernovae are even more energetic than typical supernovae and are often associated with rapidly rotating stars and black hole formation. Electron capture supernovae occur in intermediate mass stars and involve the absorption of electrons by atomic nuclei. Remnants. After a supernova, the remaining core becomes either a neutron star or a black hole. Neutron stars are incredibly dense, with masses greater than the Sun compressed into a sphere only about 20 kilometers in diameter. Some rotate rapidly and emit beams of radiation, becoming pulsars. Black holes form when the core is too massive for neutron degeneracy pressure to support. Their gravity is so strong that not even light can escape. Supernovae and life. Without supernovae, life as we know it would not exist. The elements necessary for life, such as carbon, oxygen, and iron, were formed in stars and distributed by supernova explosions. In this way, supernovae are directly connected to our existence. Stellar evolution. Stellar evolution describes the life cycle of a star from its formation to its final stages. This process begins in a nebula, a vast cloud of gas and dust, where gravity pulls material together to form a protostar. As the core temperature rises, nuclear fusion starts, and the star enters the main sequence phase. During this stage, it fuses hydrogen into helium, producing energy that balances gravitational collapse. A familiar example of a main sequence star is the Sun. As the star exhausts its hydrogen fuel, its evolution depends on its mass. Low to medium mass stars expand into red giants and eventually shed their outer layers, forming planetary nebulae and leaving behind white dwarfs. However, massive stars follow a more dramatic path. They expand into supergiants and begin fusing heavier elements such as carbon, oxygen, and silicon in their cores. This process continues until iron is formed, which cannot produce energy through fusion. As a result, the core becomes unstable and collapses under its own gravity. This collapse triggers a supernova, one of the most energetic events in the universe. In a Type 2 supernova, the core collapse leads to a powerful explosion that ejects the star's outer layers into space. In a Type 1, a supernova, a white dwarf in a binary system accumulates matter from a companion star until it reaches a critical mass and undergoes a thermonuclear explosion. Supernovae are crucial for dispersing heavy elements into space, enabling the formation of new stars, planets, and even life itself. The future of supernova research. Modern astronomy is entering a new era, with advanced telescopes and detection systems capable of observing supernova in unprecedented detail. Future research will focus on understanding the earliest stars, the role of dark energy, and the mechanisms behind different types of supernovae. Supernovae are stellar explosions that, although they seem like destruction, represent transformation in the universe. They create heavy elements like iron and gold, essential for the formation of planets and life. These elements spread through space and give rise to new stars and worlds. Everything that exists, including the human body, comes from ancient stars that exploded. Thus, supernovae show that the universe is in a constant cycle of death and rebirth. The world is full of hidden stories, and here at Paint Facts, we reveal the most impressive ones. So subscribe to the channel and turn on notifications, because the next fact might just surprise you.